हेलो दोस्तों, आज के इस एक्सप्लेनर में आपका स्वागत है। When we picture modern civilization, we usually think of these massive feats of engineering, right? Skyscrapers touching the clouds, endless highways, giant bridges. But there's a hidden heavy cost to the very foundation of a modern world. Traditional concrete infrastructure is actually a massive contributor to the pollution crisis that's literally playing out right in front of our eyes. So today, we're going to tear down the myths surrounding our go-to building materials and explore how science is engineering a completely new green reality for the future of construction.
All right, let's kick things off with a number that should honestly stop you right in your tracks. 8%. Yep, cement production alone is responsible for up to 8% of all global carbon dioxide emissions. Just to put that into perspective for a second, if the cement industry were a country, it would literally be the third largest emitter on the entire planet. Crazy, right? The traditional way we make cement involves heating limestone to these extreme temperatures, which chemically releases massive amounts of CO2 directly into the atmosphere. It's a critical environmental threat, and with global construction booming everywhere you look, we just can't afford to keep building the way we used to. We absolutely need an alternative, but, well, there's a lot of hesitation out there.
See, for years now, there's been this lingering dogma in the construction world that sustainable or green concrete is, well, fundamentally compromised. People just assume it's got lower strength than the conventional stuff. They think it's way too expensive for real-world large-scale projects. And honestly, the worst part? They assume it simply won't last as long. But the truth is actually very different. Engineered mix designs can achieve equal or sometimes even higher strength. Plus, by utilizing industrial byproducts, it becomes incredibly cost-effective. And as we'll see with the hard engineering data in just a bit, it actually offers superior resistance to harsh environments.
So it really boils down to a pretty stark choice between two completely different paradigms. On one side, you've got traditional concrete. This gives us that massive carbon footprint, puts the steel reinforcement inside at a much higher risk of corrosion, leads to super frequent, expensive repairs, and of course heavily depletes our natural resources. But on the flip side, sustainable concrete offers a radically different reality. We're talking about significantly lower CO2 emissions here. We're talking about a material that actively resists corrosion, which means a way longer service life and way less maintenance for us. And crucially, it champions the circular economy by using waste materials, like crushed concrete from old demolition projects, which really helps conserve our virgin natural resources.
Section 1. The power of blends and building a dense microstructure. Let's get into it.
You see, when we stop relying entirely on traditional clinker, that's the super carbon-heavy baked foundation of standard cement, and we start replacing it with smart alternatives, we actually change the very DNA of the concrete. By bringing in supplementary materials like fly ash, which is just an industrial byproduct, we can completely transform the mix. Studies actually show that incorporating up to 30% fly ash can cut CO2 emissions by a staggering 50%, half. But it gets even cooler with this groundbreaking blend called LC3, or limestone calcined clay cement. What LC3 does down at the microscopic level is create this highly refined, super dense pore structure. It acts almost like an impenetrable microscopic shield, making it incredibly difficult for harmful elements to ever get inside.
Moving right along to Section 2, Biology meets engineering with self-healing bioconcrete.
Imagine if we could push the boundaries even further and create a building material that actually heals its own wounds. Seriously, concrete naturally develops these tiny microcracks over time, and that allows liquids to seep in and rust the steel inside. But in bioconcrete, special dormant bacteria are mixed right into the foundation from the very beginning. It works in this fascinating four-step process. First, a microcrack forms. Second, water enters that crack. Third, that water actually wakes up the dormant bacteria. And finally, they activate, start munching on their built-in food source, and begin to precipitate calcium carbonate. That's limestone. These bacteria quite literally produce limestone from the inside out, completely and permanently sealing the crack and automatically recovering any lost strength. It is an active, long-lasting, and ecologically beneficial repair system. Mind-blowing, right?
Okay, Section 3. The hard data, proving the durability.
Now, biology is absolutely incredible, but let's be real. In the construction industry, everything ultimately relies on the hard numbers. What we're looking at here is the electrical conductivity of different concrete mixes over a curing period of 365 days. So why does this even matter? Well, it's actually a scientific proxy for how easily harmful chloride ions, like salt from the ocean, can penetrate the concrete. Notice that blue line up at the top for ordinary Portland cement? It is incredibly high. But then check out the red line for fly ash and that black line right at the bottom for LC3. The electrical conductivity drops massively. In fact, the chloride diffusion coefficient for LC3 is up to 93% lower. This basically proves that these sustainable blends create an incredibly tight matrix that actively blocks corrosion.
Which brings us to the real knockout punch of this whole thing. 10 times. Based on life cycle assessment models and that hard data we just talked about, using sustainable blends like LC3 and fly ash can extend a structure's service life by up to 10 times in harsh, chloride-heavy environments like coastal areas. Just think about the massive implications of that for a second. A bridge pier that might normally need massive repairs or even replacement in a few decades, it could potentially last for centuries. That is 10 times less maintenance, 10 times less rebuilding, and a massively reduced carbon footprint over the entire lifespan of the structure. It's an absolute game changer for civil engineering.
This is the exact kind of world we could be building right now. We've seen the massive 8% emissions footprint of traditional cement, but we've also seen the incredible realities of LC3, dense microstructures, and those amazing self-healing bacteria that can extend structural life by 10 times. The science is here, guys. The data is undeniably clear. So I want to leave you with this final provocative thought. क्या अब भी हम पुराने polluting concrete पर अटके रहेंगे या sustainable future चुनेंगे? Will we still stick to old polluting concrete or choose a sustainable future? The choice is entirely ours to build. Thanks so much for joining me on this explainer. See you next time.